Hi, everybody. Can you hear me? Yes? Awesome. Well, thank you for joining us today. My name is Ana Pinheiro-Privet, and I am with AWS. I'm the head for sustainability at the AWS Impact Computing team, and I'm also the global lead for the Amazon Sustainability Data Initiative. So I'll be showing you a few slides and say a few words about the program just to set the context. But then we have one of our customers joining us today from TerraPulse to give an example of how the data and the resources we're making available through this program are creating impact out there. OK, so let me tell you a bit more about ASDI, or the Amazon Sustainability Data Initiative. So ASDI is an Amazon Tech for Good program. And I start there by saying it's a Tech for Good because I really want to convey the idea that we are trying to understand how to use our scale and our infrastructure and our technology to really bring that to the community and help create more innovation in the space of sustainability. And this is partly because, there's no surprise that we're all trying to solve these big sustainability problems like climate change. And Amazon has made extensive commitments in that space as well, not only to commit to going carbon neutral by 2040, which is 10 years ahead of the goal of the Paris Agreement, but through that, there's a lot of innovation and work that we need to do to basically turn our operations upside down and make sure that we remove as much carbon from it as possible, become more energy efficient, and do all the things that are required to meet this commitment. But one of the things that we are experiencing as we go through this sustainability transformation is a challenge with data, right? And I'm saying this because this is the problem that ASDI is trying to solve, is the data problem in sustainability. I don't know the background of the people in this room, but I have the feeling that most of you have experienced the challenge of finding and using data for some application. And that's what we hear consistently from our customers and what we experience ourselves. We have more data than ever before. From more satellites are being launched. Models are generating more higher resolution data. We have IoT devices everywhere. And this is creating an exponential increase in the data that is available. But that is not necessarily translating into more insights and more easy insights to make decisions and inform policy for sustainability. The other issue is that a lot of these data sets are extremely big, right? We're talking, for instance, when we look at climate data or satellite data, we're talking terabytes and petabytes scale of data, which not everybody is able to actually host the data and then analyze it. And the data is dispersed everywhere. So if you want to solve a problem now, you probably have to identify several sources of data, go figure out how to get it, and you have to acquire it, you have to store it, you have to clean the data, and only after that you're actually going to generate some kind of knowledge or insight that is going to inform whatever problem you're trying to solve. And we see that this is a redundant process, right? Everywhere around the world, people are doing this repetitive effort, which we call on AWS the undifferentiated heavy lifting. So this seems like a great opportunity for us to use the cloud, step back and say, OK, how can we actually tackle this issue and remove that effort so we can start operating at a higher level and generate insights and knowledge to help us tackle these big issues? And this is exactly how ASDI was created. We're trying to significantly reduce the cost, the time, and the effort that it takes to get these big data sets and then extract knowledge from them. So the kind of the premise that we have behind this really requires a bit of a change in the way that data analysis and science in general is conducted. The traditional method is you find those data sets, you bring them close, normally to you in your on-prem space. You do your analysis, and then if you have data that you want to share with others, you need to find a way to make that available. And forget about even sharing your code. That's another issue, right? So what we're trying to encourage here is a bit of a shift, where instead of taking the data and spreading it everywhere, we bring kind of golden copies of the data to the cloud, and we make them free and openly available to anybody. And the value of that is that now the data is next to all the compute and all the services available on AWS, which make it much easier to actually experiment and do analysis on the data. So what exactly is ASDI? So we built the program on top of 3 core areas. The first one is data democratization. And that's exactly what it is. We work with the community, and when I say community, we really work across all the sectors, so as much with private sector and nonprofits, academia, governments, and we try to understand what are those foundational data sets. For instance, if we're studying climate change, what are the data sets that the community needs? And those are climate projections, historical weather records. We need satellite, for instance, information to assess the asset distribution on the ground or study deforestation. So we identify what are those data sets. And then we work directly with the data providers and bring the data to the cloud and make it open and freely available to anybody. So one key thing that we make sure that we adopt here as part of our philosophy is that Amazon never touches the data. So when we create this model, we cover all the costs for storing the data in the cloud and all the egress costs if somebody wants to take it out of the cloud. But the data provider, let's say NASA or NOAA, owns the bucket in the cloud. They maintain it, they distribute it. The only commitment they have to make is that they make it free and open to anybody in the world. And so we have now petabytes and petabytes of data. I can show you a little bit more in a second. So that's the data part. So imagine now in this ideal world, we have all the data that we need to solve these problems in a cloud environment accessible and free. But the reality is if you want to use the data in the cloud, there's some compute required with some costs associated with it. And we don't want that to be an impediment for innovation to happen in this space. So what we do is we have a dedicated cloud grant program that basically is open to anybody. Anybody can apply. There's really no limit as long as you can justify it. And if it gets approved, we cover the cost of working in the cloud for a period of a year. And the basic requirements that you are working sustainability and ideally on top of one of the data sets that is in the cloud. And then the third one is very focused, is equally important, if not more important, which is we have the data, we have the compute, but we need to actually build a lot of this knowledge space, right? Especially in the sustainability community. We need to basically share with each other what we've learned about the cloud and open data can lead to solutions. And that's a lot of mechanisms that we use there to encourage people to tell their story, write blog posts, share their code if they can, write tutorials. So there's a lot of things going on that third component. I'm just going to go very briefly through this because we really want to hear from Joe, but that's basically the mental model. If we open the data, put in extra compute, offset the cost of experimentation in the cloud through the grants, we'll create more knowledge, and hopefully that will actually create a flywheel. Some examples of organizations we work with, we have over 100 data sets in the cloud, petabytes, as I said. They're organized right now in about 14 different categories. These are just examples of some types of the data. And the really impactful thing that we think is excited for ASTI and for all of us is what happens when you open data and put it in the cloud and actually make these resources available. And what we see is, we see a lot of, for instance, of startups that once we cut the cost of acquiring the data and storing it and maintaining it, can just easily build some workload on top of it and turn it on and off as much as they want. And we have so many different applications. These are just some examples that goes beyond the private sector and the startups, but all the way into nonprofits and government as well. So I am going to stop and ask Joe to come here to the stage. But please, if you're interested in looking at all the data sets we have available, feel free to go and visit our page. Also, this week, we announced basically the integration of the ASTI catalog into the AWS Data Exchange. And what that means is that now we have all this open, free data in the same service as the licensed data and for data that you can actually buy. And that's great because you can find it all in the same basically searchable capability. And the last thing I'll mention is we launched also a hackathon to use all this data, focus on sustainability solutions in partnership with UNESCO. If you're interested in learning more, please go to our booth downstairs. It's the first one, and you first get into the showcase session space, and we'll be happy to tell you more about it. So thank you. Okay.
Thank you, Anna. Mic check. Am I good? All right. So my name's Joe Sexton. I'm actually an ecologist. I started out in wildlife ecology and conservation. and saw my first satellite image in 1998. Held my first GPS unit, saw my first satellite image, and saw my first GIS software. That led through a long chain of events to where we are now, and I'll take you through a personal narrative. The compression rate will be very high, and culminate kind of in how ASDI is helping us and what we're doing with it. So let me start out with some elevation between us and the planet. Welcome to the Anthropocene. The human population is almost at 8 billion. We'll get there about 2025. We're growing at 1.1% per year. Life expectancy is up. Poor people are, the demographic processes are different. Lower mortality in infant cohorts in poor populations, longer lifespans in rich countries. The economy is $88 trillion per year, gross world product, and we're at about 2 billion websites and 5.3 billion internet users. This is actually pretty good. I mean, not so much if you're an introvert, but the question here is not for humans so much, it's the rest of the planet, and thereby eventually to humans. So 75% of Earth's surface is directly altered by human beings. 20 to 40%, depending on how you do the math, of terrestrial net primary productivity is appropriated by humans. So net primary productivity is the carbohydrates fixed by plants for the sun after respiration. So think of it as biomass. 98% of terrestrial vertebrate biomass is us and the animals that we eat, livestock. 50% of Earth's accessible freshwater resources we use. We move more soil than plate tectonics. And we supply more plant-available nitrogen to the terrestrial ecosystems than all natural processes combined. Interestingly, this is increasing plant species biodiversity across 2/3 of the terrestrial biosphere. That's a local process. It's down globally, but the mixing rate is up locally, so if you think of suburbs and everything, you go, this hotel, for example, has more biodiversity than the background processes. It's all moved from somewhere else, and so those processes are causing extinctions. And that extinction rate is about 1,000 times the historical paleontological background rate of extinction. Now, as a planet, we've been here before. As humans, we've been here before. There are many studies on what causes populations, human civilizations to boom and bust. And we have, spotty archaeological records. The Indus civilization, climate change, agricultural failure. The Anasazi, not far from where we are now, drought. Rome, not so much climate related. This was expansion of the empire, assimilation of the cultures, but overextension of infrastructure coupled with a lot of other things, eventually led the fringes to deteriorate and collapse in. The Maya, lots of different accounts, but one of the leading ones is deforestation. Greenland Vikings, climate change, and Easter Island was deforestation. So about 2000, Jared Diamond published a book. He's actually a community ecologist, started in birds and moved on to humans, as you do. And the thesis of his, he gave a lecture in Utah. I was a graduate student at Utah State University. I traveled down to Salt Lake City, a gigantic room, and he ended with this point that islands, he focused in this book on islands, the largest islands tend to not have these boom and bust. The stochasticity is averaged out over large islands, and those civilizations tend to not have as variable dynamics. Really small islands tend to not the really small islands tend to be lost because of that stochasticity. And arrogant little self in the back of the room raised my hand and said, well, what is Earth? Are we a large island or a small island? And I was very proud at that time to have stumped Jared Diamond. He kind of went, what are you even talking about? But the point for this room here is we now have the ability to turn Earth, a big island, and combine that with the small island where we can see the entire border and we can know what's happening inside of our island. So the point is that it's different this time. All those civilizations of the past, and I do not mean this facetiously, we have the internet. And a keynote speaker a couple days ago said, why did the dinosaurs go extinct? Because they didn't have a space program. This civilization has a chance to not go extinct because we have a global network of information and the ability to respond as if we were on a small island, but with the benefits of a big island, right? We have the globalization to move resources from one location to another, but we have the ability to not lose sight of, say, our forests or our agriculture, et cetera. And specifically, shout out to the Amazon Sustainability Data Initiative is accelerating the pace of innovation to do this, because we really are at the beginning of a generation. So let me start, there's that kid, let me start at time zero for those of us that use a specific satellite, Landsat. So Landsat, a series of satellites, 1972 to present, they're up now. 1984 is when Landsat 5 got launched. It was supposed to be a 5-year mission. It lasted for decades, and it actually gave birth to the field that I studied in my PhD, landscape ecology. And it allowed landscape ecologists to start seeing ecosystem dynamics. We are able to see things change over time. 2009 is when the USGS and NASA made the entire global Landsat archive free and open to the public. So for what we do, this was time zero. At that time, I had just finished my PhD, and I joined a lab, the Global Land Cover Facility, where I met Min, who promptly put me out of a coding job. And GLCF got a contract from NASA to take these data, so that's the world's first global mosaic of satellite imagery created by Min, and turn it into this. That is the world's first 30-meter resolution map of tree canopy cover. Every pixel is a percentage of canopy cover, whether it's deciduous, evergreen, completely agnostic, insensitive to species. The reason, the impetus behind that was to look at large-scale land cover and land use changes. That's the red there are significant changes of forest cover between 2010 and 2015. So that was the first global 30-meter resolution map of tree canopy cover, and by implication forests as well. And we did it over multiple points in time so that we could map the changes. So you're looking now at the arc of deforestation, which is actually one of the first real big publicly visible uses of these data, long before us. But so not to get too deep into the geek, the way that we do this is we're pulling data from 250-meter resolution satellites, 500-meter resolution satellites, both at daily update frequency, spectral reflectances, red, green, blue, near infrared, a couple middle infrareds, and a thermal, combining those with soft training data. So we did this, and frankly, we surprised a lot of the scientific community, because the typical way of doing this is taking necessarily, you don't want it to be, but a small sample of very highly reliable observations, your truth training data, and then fitting a model and extrapolating it out. What we did is took multiple sources of truth, degraded them in a sense to their underlying probability density functions, and then fit our models on these uncertain training data that allowed us to in every pixel estimate or represent tree canopy cover as its own, in this case, normal probability density function. Tree canopy cover, the map, the first map that you see is the expectation, the mean of the density function. Then below that, which few people actually want to see, is the uncertainty map. And it's the standard deviation is the root mean squared error of the regression tree. And so we use those two things together, and that allowed us at that time, right when although the Landsat data were free, there was no architecture to really get them and use them and really have a really fast pace of development. So we could map the entire planet of what we know and then the known unknowns, what we don't know, which allowed us to allocate our resources and very quickly skip over the places. We don't need to keep working in the middle of the Sahara. We don't need to keep working in the middle of the Amazon. And to tell you, I mean, we ended up like spending a lot of time on savannas because the definition of forest is a fuzzy boundary on percent tree canopy cover, or on shrublands, right? Is a shrub a tree? Is a shrub not a tree? And then change, so converting from percent tree canopy cover to categorical forest cover, we just take the integral of the probability density function above the threshold that we use to set forest. So United Nations Framework Convention on Climate Change allows entire countries to define what it means to be a forest in that country. And they do that by setting a threshold on tree canopy cover. What we did was give everybody a global high-resolution multi-temporal map of tree canopy cover, allow them to set their threshold, and then the probability of every pixel being a forest is the integral of the probability density function of tree canopy cover in that pixel. So it allowed us to take one, very noisy, uncertain training data, as well as noisy, uncertain satellite images. Different seasons, we've got cloud cover, we've got snow cover. In every case, we're trying to remove that noise, but it's models on top of models, it's turtles all the way down. And so to the degree possible, we're representing that uncertainty and propagating it through to get these maps where we remove the clouds, we remove the phenological, the seasonal variability, and come up with these consistent maps. And there's that map. That the top one is the certainty of tree canopy cover estimation, and the one below is the certainty of the forest cover maps that come from that. And there it is. That's, I think, figure 1 in the paper that came out from that, the world's first global tree canopy cover map at 30-meter resolution. And since then, we've moved on. We can use that uncertainty to do change detection over time. So the standard way of satellite remote sensing, land cover remote sensing, change detection is to take a map, you apply your machine learning, time 1, you take your satellite imagery, apply your machine learning, time 2, and just look for categorical differences, image differencing. If you don't take into account the noise in that signal, you end up seeing a lot of differences in that's unincorporated variation. So what we're doing now is we're taking this probability of forest over time and then essentially doing a time serial t-test, looking for changes in a kernel that apply a significance criterion. And once we figured that out on trees and forest and deforestation, degradation, all these things can be translated into that ontology. Then we turned around and did it for surface water. And then we did it for impervious cover and urbanization. And then we turned around and did it for wildlife habitat and biomass and fire risk. And just as long as we have a semantic or an ontology that allows us to define the classes and then the relationships between them, and we can propagate that uncertainty, then we're slowly accreting this universe of different data sets that feed from each other. And every time now we produce a map for one region, then it can ingest those data as either covariates or stratification covariates or regression covariates, or as training data, and the network of these data sets expands and grows in certainty. So 2013, that's when we published the paper. Those are the three co-founders. We were all at that University of Maryland lab. Chief scientist, me, Min's the man behind the curtain, and Sarb's the CEO. And in 2014, we founded TerraPulse with the point of getting this information out of the ivory tower, out of the DC Beltway, and then out into just everyone's hands, right? Because adaptation, if it's only governments and if it's only universities, the economy has veto power. I think we've seen that in elections. Everybody has to go in this together, or those that are disenfranchised by the information gap are going to find ways to slow the process down. So we literally do aspire to get this out to everyone. So TerraPulse, I mean, this is not an uncommon kind of flow chart for a company like ours. We take the tabular data, the GIS data, satellite imagery, put it through machine learning, make these global maps. The way that we do this is unique so that we can do the time series analysis on maps, and then we export them and we serve those data to these different land use industries. What I'm going to talk about in sort of a case study here is an application in biomass and wildfire right now. So if you read the news, carbon markets are really gaining traction, and entire countries are needing to register their forest carbon assets, their natural capital, onto carbon exchanges. So they need to know their baseline conditions, their historical changes, all these things that I'd like to say that we thought, we knew ahead, but really we just did it in the way that we thought was right, and the economy has grown up around us. And then, the other side of the news is the wildfire crisis. So we're going to talk about the Olympic Peninsula. And usually when I give this demo, I'm usually sitting in front of my computer on a Zoom or a Teams meeting or something like that, and it's very interactive. So these are really just screenshots of TerraPulse's platform. So if you've got a TerraPulse account, you hit login, and we're a data company. We're not really an interface company, but the point of the interface is to allow people to sort of take the pulse, right? Check the pulse of the planet, see where they are, go wherever they need to, where they have an interest in the land use. And there's that. This is the 2021 version of that original 2000 tree canopy cover map. We're now pulling in addition to Landsat and MODIS, we're pulling in Sentinel, which is a European Space Agency pair of optical sensors that have about a 5-day repeat frequency. So it gives us a much denser temporal sampling to remove the clouds and remove the noise. And we're now at 10-meter, standard 10-meter annual monitoring resolution, although we have in cases where say the cloud cover we get a really nice open cloud-free season, we can narrow that down to within the year. So let's look at the Olympic Peninsula. Let's see if that works. Okay, so there's Seattle, Tacoma. This is Olympic National Park, big, dark, dense green, really dense tree canopy cover. And around here is timberlands, so a lot of turnover in the forests. We can break this down because we can see the progression of vegetation canopy throughout the season, and we can discriminate between deciduous tree canopy and evergreen. Deciduous trees lose their leaves. This is a percentage of that. So this inherits from tree canopy cover as well as the phenology in the year. And you can see, let's go back. So again, there's Seattle, a bunch of planted ornamental deciduous trees in people's yards. These riparian areas are full of alder and big leaf maple, but really the Pacific Northwest it's an evergreen coniferous forest. So again, you've got, your Douglas fir plantations are a major portion, and then your wildlands, you've got the national park, and these are the Cascades. So there again, so 2010 to 2015, this is the same algorithm that we mapped the deforestation of the Amazon shows us for any slice of time, right? We can say 2010 to 2015, we can say annual, we can do much longer periods. You can see there's very little clearing in the national park. This is actually a national forest around the ring of the national park. Very little clearing currently there, and you've got a lot of clearing in these timberlands. Cities tend to not have it. If you see clearing in a city, it's usually urban development. That pinned location, this is the daily 500-meter resolution. It's called the Normalized Difference Vegetation Index. It's a normalized ratio of near-infrared and red reflectance. Chlorophyll absorbs red, reflects near-infrared. So by taking the balance of those two solar reflectances, we can get an estimate of how much chlorophyll is in any location. So that's daily, goes back to 2000. It's obscured by the menu there. The dips are usually snow, but it's very, very stable throughout the year. That's how we can infer that it's evergreen. It's high. If I were to show you a desert or something, it would be down here. A deciduous forest will do this. And then you can see in, 2021, there was a thinning or a clearing of that pixel. Again, these are 500-meter pixels, so we're usually seeing sub-pixel clearing at that resolution. It progressed throughout the year and then slowly on a climb back to within the historical one standard deviation range of variation. Now, if I run that algorithm, that change detection algorithm, all the way backward to 1984, it gives us a map, a detection of every year that a forest was lost. This heat map is the year of most recent significant forest loss. And by significance, I mean exceeding the noise bounds that we put on it from all of the information that we can bring into it. And you'll notice that, again, the national park, the only places where forests really get lost are avalanche chutes. Around in the national forest, there's a lot of yellow, but not a lot of red. Red is more recent. That yellow corresponds to the passage of, well, first of all, the listing of the spotted owl on the endangered species list, and then the passing of the Northwest Forest Management Plan, which severely curtailed logging in the national forests. So we can see policy in these ecological data. So the yellows stops in about 1994, and then a lot of that forestry continued on, and the argument can be made that it moved out into those private and state-owned timberlands. Tremendous effects on the human economy, and obviously tremendous effects on the ecology as well. So if we run that same forest loss algorithm logically backward, we can also get the year of forest gain, right? So we just look backward until we don't see forest, and then we go forward until we do see forest, and that gives us a year of the year of forest establishment or forest gain. So for that box, this is a histogram, a frequency distribution of all of the 30-meter resolution values in that box. It's about the size of a county in Washington State. There's your tree canopy cover, density function, or your frequency histogram, and that bottom histogram there, forest gain, in forestry, that's called an age class distribution. That data there drives projection models, supply chain, sustainability understanding. If you want to know on the very reasonable assumption that a forest that is 10 years old this year will be 11 years old next year, you can run that histogram forward with your known regional harvest rates, either for a region or for an individual company, to know if there are going to be supply chain constraints decades into the future. And collecting that data in 1998 when I did that on the ground would have taken a lifetime. I'd still be out there trying to do it. Or I'd be resorting to a sampling approach where I'd take, a forester would take 10, 100, maybe 1,000 points over that kind of region and then building it up, but not with this and not in 1 second of processing time. So as I said earlier, when I was talking about kind of how the algorithms are laced together, we can also ingest training data on biomass. And there are many, many sources of it. The one that this is using is the JEDI instrument. It's a photon counting LiDAR, a laser scanner bolted to the space station. And it's going to ride there for about, I think the mission lifetime is about 3 years. And we can intersect that data through our temporal stack of all of those covariates and get an expectation in that pixel of the biomass. And if we get other data sources, we can assimilate those as well. And then down to really like 30 or even 10 meter resolution, we can just interrogate those data. A user can interrogate those data. And in this case, we've got 36 tons in that pixel. But let's go over to out to the east. So this is the Olympic Range, the Coast Range, very wet, very dense, very low. The only real disturbances are, the biggest disturbances are forest harvest. But out here in the Cascades, we've got much different ecology. This is on the limits in many cases of where a tree can exist climatologically, and trees don't die passively. Something kills them. Either a tree will get stressed by drought, and then beetles will attack it, and then it dies, or the tree will get stressed by drought or something else, and lightning will strike, or somebody throws a cigarette out of a window, and you get a forest fire. So backing up a little bit, talking about the kind of the expanding utility in the market for these sorts of data sets. Carbon markets are, they're in the news everywhere right now. The Trillion Trees initiative, right? We're going to plant 1 trillion trees across the entire planet. Well, that's excellent. We should be doing that. However, not all pixels are created equally as a location sustainable for trees. There are some places that humans cut the trees and they're not there anymore, and you can grow trees, but some, it's just climate won't support trees. The mechanism for removing forests is typically fire. So let's zoom in on that location, and you can see there's, you've got these canyons where the sun angles are different, and you can get more trees. You've got more water flowing into that location from the higher elevations. The ridge lines have lower biomass. The canyons, the river bottoms have more of the riparian areas. And you've got a little bit of, looks like timber harvest right there. I think that's a town. And this is what's so much fun for me is my 22-year-old ecologist gets to go be an ecologist globally anywhere in the world. Now, we can take through the satellite record, that daily data that I showed you before can also show us when a forest has burned. The vegetation drops quickly, the temperature spikes, then it goes back and you get this sort of signal of ecological recovery. So, and we don't actually do this ourselves. This is gotten from another data set. But we can mine backward through the satellite archive and find the history of fires, and then relate that incidence to either the coincident data from our own time cube or the antecedent conditions. Fires have this funny behavior of changing their own environment. So if you get the timing wrong, and if you're not doing full time series analysis of your data, then you could miss, if you collect your predictor covariates after the fire, you've obliterated any sort of your predictive ability. So we kind of over the decades have had to build this time serial very rigorous, robust way of propagating the uncertainty and making the maps so that we can eventually get to this stage of biomass and now fire, a highly dynamic process. So this is a heat map of the probability given, this is danger, so this is the probability of that pixel burning in 2020 given the fuel, all those vegetation data, the terrain, and the meteorological data. So terrain doesn't change enough, we can take a static layer from that. The vegetation fuels, those change very dynamically, so we take the most recent clear observation that we can get, and then the meteorology is, right now we're just doing it as the coincident, the day of, although there certainly is a lagged effect there that we could explore. So that's a map of fire danger. Now, fire risk that I'm not showing, this is kind of begs an interrogation of what we mean by probability. Wildfire hazard, which is just off the top of the screen, is also a probability of fire, but it's the probability of fire given fuel and terrain, right? So you can look at a fire hazard and you're not really taking into account the weather. And that's useful for fire management if you want to clear the forest, right? You can't change the weather, but you can change the forest, and this gives you a map of where you're going to have the largest effect on the ecosystem by doing that. Danger, that's when you drive into the national forest and you see the Smokey Bear sign, fire danger is high today. That's because it's incorporating the meteorology. Now, let's shift a little bit into the use case and think about those carbon markets again, right? So there's a concept in finance called value at risk. If we were to take that biomass map, and we did, and multiply it by our probability of fire in a year, this gives us a map of the assets at risk, value at risk of the ecosystem. We don't have to do this for biomass. I did it for biomass here, but you can do it if you want to do your accounting in tree canopy cover, if you want to do your accounting in forest cover. If you've got a map of property value, then you can multiply that asset value by the hazard or the danger, however you like it, and get a map of value at risk. You can do this for mule deer habitat, and we've done that. If you have a fire, how much of your asset, your natural capital, will be lost. And then we can zoom in. So again, we're talking about very high resolution data, and zoom into individual timber management parcels, get that information, and serve that out to intersecting with a property parcel database, and serve that either to the government agencies to allow them to look at their entire state or country, or down to individual landowners, right? Like, you own this land, and increasingly a lot of this land is not owned locally. Someone owns the land and lives somewhere else, and this gives every landowner the ability to really adapt to climate change, right? The title of the talk is not not stopping climate change. That's another talk. This is about adaptation, right? The world is changing, and how do we get information from satellites measuring near infrared radiation to into the hands that can actually convert that power into action? So insurance companies across the board. So actually, to go through that, we're still, as far as TerraPulse is concerned, I don't do the accounting, much to the chagrin of my CEO, but we're doing a lot of serving this data to scientists. We work with wildlife biologists, forest ecologists, watershed hydrologists, right? All of this, to the degree that the ecosystem components, the hydrology, the meteorology, the wildlife, the biodiversity are all coupled. All this information is just passing back and forth between these different scientists. To governments, this is the obvious next step. And governments have been using these kind of data for a very long time. As the history of satellite imagery has gone from 2 kilometer and 1 kilometer data down to 500 meter resolution, down to 30 meter resolution, down to 10 meter resolution, and satellites now are up at less than 1 meter resolution. The governments have been aware of this and have been using this for a long time. National forest inventories. TerraPulse is working with several countries. We've mapped the Philippines, we've mapped Myanmar, we've done this for the Dominican Republic, Costa Rica, Chile now, many of them, because a lot of these large land-owning, land-managing entities are trying to register their assets in these carbon markets to basically, in effect, increase the value of the forest by adding another use case for it, right? For conservation. A lot of it is being served by that. Nonprofits, land trusts, again, any organization that has an interest, has a stake in land and being able to change it over large distributed areas. And increasingly, this is where the real action's at, where the real growth is at right now. Because, science, we've known these kinds of things for a long time. We haven't been able to do what I just showed you what we can do. And governments, again, they know it. They've managed large acreages. But it's really the businesses, so timberland investment, that right there, that's the equivalent of a Zillow home report for a forest anywhere in the world. Real estate brokerage, and as you can see through that wildfire example, hazard insurance as well. So this goes back to the overarching question: is this human enterprise, 8 billion people, all logged into or 66% or so are logged into the internet, ingesting all this information? Is this sustainable? I cannot say, right? That all I can do, all TerraPulse can do, is provide better data to empower other people to make their own decisions. We don't prescribe the decisions. We give them the decision, or we give them the power to make their own decision. And with that, I'll take any questions.
Can you hear me now?
Yes.
Yeah, so we'll be hanging at the booth downstairs. You can certainly follow up with Joe or with myself if you have any questions, but also feel free to stop by the booth for the rest of the afternoon and learn more about what we're doing and groups like Joe are doing with the free and open data in the cloud. So yeah, thank you for coming.